All right, good morning. All right, so how is everyone today? Pretty good, that's good. So any questions? Sleepy, I can relate. Any questions on what we've been doing so far? We're starting to talk about dynamic memory and dealing with pointers in dynamic memory. All right, well let's review our basic setup. So we have a node, and it's going to have a data field, which will continue to be an integer, and it's going to have a next field. PA1 next was an int, PA2 next is a pointer, and it points to some struct node somewhere. So the declaration of a struct node tells us that part of this structure includes a pointer to another thing that is also a struct node. Could be itself, will probably be something different, a different node, but it doesn't really matter. All we're saying is that this is a pointer to something of this type. It's not recursive in the sense of the compiler can't handle it, because remember, a pointer is just an address. And all we're saying is that this field called next has a memory address in it. It happens to be a memory address that's pointing to one of these type of things, but it's still just a memory address, and that's all the compiler needs to know to be able to put things together. It knows, in our case, it's going to have to allocate 8 bytes for that. So if we want to create a linked list using these nodes, let's set up a sentinel node. And normally, instead of int sentinel, we would say struct node sentinel. But we're going to do something slightly different. Almost any time that we deal with these nodes, we're going to be dealing with pointers to them. And when we want to interact with a node, when we want to print out its data field or check its next field or something like that, we're going to do it not by actually grabbing hold of the node itself, but by using a pointer to the node. And we'll see why that makes sense as we go through the next few days. But I'm going to actually declare sentinel to be a struct node star. All right, so let's sidebar and talk about pointers. And I want to play with this in GDB. So I'm going to make an integer I. Let's see. So on a car star, we cannot assign a value string equals foobar. Why won't we define structs? Actually, if you set up a car star, you can set that equal to quote foobar. In fact, that's a pretty usual thing to do. And it's a good analog to what we're going to do with pointers. But what you can't do is if you have you can't change what's stored in a location that was defined inside double quotes. That's just preserving strings. Hey, glad you're here. All right, so let's make a pointer to an integer, and let's let's assign a value to the thing that that points to. And I want to do this in the debugger so we can kind of see how this works. Alright, so this is just code to play around with, right? Here's my integer star I. I'll print out a message when I'm ready to set this thing equal to 15. I'll do the assignment statement, and then I'll print out a message when I'm done. I'm mostly putting those prints in so I can set breakpoints there inside GDB. So let's compile that. And let's run it in GDB. Alright, so I'll say start. It's about to say ready to do assignment. I'll let it print that message. I'm about to set star I equal to 15. Right, so I'm ready to execute this line of code. Alright, let's take a look at the current value of I. Guess what? It's a 0. Why is it a 0? Because I never gave it a value. Right? If I didn't have an asterisk here, if I just said integer I, and then I tried to print the value of I, there's no telling what I'm going to get. Sometimes you get a 0, sometimes you get negative 32,000 something. Sometimes you get a big number around 2 billion. Right? So I is declared to be a pointer to an integer, but I have not initialized I itself. And it turns out that I is equal to 0. And when I print it with the print command, GDB knows it's a pointer to an integer, so it's displaying this 0 as pointer to an integer equal to 0. I'm about to execute this statement. What do you think is going to happen when I execute that? I think that there'll be the hex code for 15 in that address. Good. What address is that going to get stored at? Right, add I will hold the value of 15. Right. Right, address 0. So this is saying, right, don't set I equal to 15. Look at the value of I, that's 0. Set the value at address 0 equal to 15. So this will set memory location 0 to 15. Alright, perfect analysis there. The trick is that memory location 0 does not exist. It's deliberately mapped to a non-accessible location in memory, so that if you accidentally try to store something at location 15, the memory management system says there is no such segment, and you get a segmentation fault. Okay, that's what a seg fault is. It's trying to access a location in memory that doesn't exist. And in this case, it's kind of a safety thing, right? It happened to be, equal to 0, which is a non-available location. So if I forget to give I a reasonable value, my code will stop very quickly. It would be worse if this was a location that was accessible, and it stored a 15 there, because I have no idea what that's going to do if I write a 15 into some random memory location, right? It could be where some piece of my process information is stored and now something weird happens. So there are memories that exist but should not be overwritten, and there are memories that exist that you are allowed to overwrite, and there are memories that do not exist, memory locations. So if I try to step on memory that's being used by the operating system, I'll generally get a segmentation fault. and it's indistinguishable from not going to a location that doesn't exist. Yeah, we're definitely going down this thing. All right, so what do we do about this? We didn't want to make a seg fault. We have to give I a value. So set I equal to a location in memory where we can store an int. Well, what value should we set I equal to? I mean, should I just pick some random number? Probably not. So our goal is to find somewhere in memory that's got enough space that we can store an integer and isn't currently being used, and that we can start to use and make sure nobody else uses it. And so this is where our friend malloc comes in. And that's exactly what malloc is there for, is to say, hey, I want some memory from the dynamic memory pool. So if we look at the manual page for malloc, right, comes from standard lib. We basically call it with a size. This is basically an integer, and it returns a pointer. Now it says it's a pointer to a void, but that's kind of a trick in C. It means it can point to anything. And so it allocates this many bytes and returns a pointer to the first byte of that allocated memory. The memory is not initialized. Okay, so we don't know what's in that memory when we get it. It's basically junk. The return value from malloc is usually the pointer to that block of memory that was allocated, but if we run out of space, it'll return the value null. And null is set up for us inside the chain of things that get included when we include standard io.h. And null is set up to be a pointer to 0. And since we know memory address 0 is never accessible, it's safe to set that as a flag in our linked list, for example, to say, hey, what's the next node in the list? Oh, it's at location 0. We can use that to say, oh, that's the end of the list. But don't ever use 0. Okay. Always use NULL uppercase if you're trying to refer to the return value from malloc that means out of space, or if you're trying to mark the end of a list, if you want a pointer that's not actually a pointer but is a flag, always use NULL. Don't ever hardcode 0. Okay, that's a grave thing. All right, so let's set I equal to malloc. And the next question is, how many bytes do we want to allocate? Well, you and I know that an integer takes 4 bytes. And so I could put a 4 in here, I could put a 16 in here if I wanted some extra space, and so on. Try to avoid coding magic numbers. Okay? What we want here is however many bytes it takes to store an integer. And we don't have to know that or guess that. We can use a keyword called size of. Okay, size of is not a function call, it's a keyword. So you use the keyword size of parentheses and then the type of a variable. So I'm going to put an edict in here. Always use size of with a type of variable, not with an actual variable. So yeah, always use size of, and then you don't have to know, is it 4 bytes or 8 bytes for a long int, and so on. And this will change, right? If I run the same code on an Arduino, size of int is 2, because Arduinos use 16 bits by default for an integer. If I run this on my current system, it's 4. If I run it on a system 10 years from now, it may be 8. That may be the default size for an integer. So size of always works. Don't ever put a variable in here, right? If you have an array that's defined as an int star, and I say size of, the name of that array, I'm going to get back 8. Because an array is a pointer, it's a memory address, and memory addresses take 8 bytes on this machine. It's not going to magically look into my array and say, oh, you allocated space for 100 integers here, I'll give you 400 bytes, right? So always use size of with a type. And if that doesn't seem like it's going to work for you, meditate on that, right? Don't just throw in the name of a variable. Think, how can I do this without using the name of a variable? How can I do this using a type? And if you just, shortcut to throwing in the name of the variable, it's probably not going to do the right thing. And it will be one of those bugs that will not show up until probably I'm testing your code. Because I'll test it more aggressively than you might. And if you put in the name of a variable instead of a type, you'll have some wiggle room that'll let you get away with things for a while. But it's really kind of a time bomb that's lurking. You're allocating space for one variable. Now, if that's a pointer to an int, this would be size of int. If it's a pointer to a car bracket 20, it would be, size of car bracket 20, or maybe 20 times size of car. If it's a pointer to a struct node, it's size of struct node. So it's always pointing to one type of thing, right? And that's the thing you want to put in size of, possibly multiplied by the number of them that you want. If it's a struct node, definitely do size of struct node. Don't try to do size of int plus size of struct node star, because we already saw yesterday that doesn't work, right? If we tried to allocate size of int plus size of struct node star, that'll be 4 bytes, that'll be 8 bytes, that'll allocate 12 bytes. This takes more than 12 bytes. This takes 16 bytes because there's 4 bytes of padding in between the data and the next field. Yeah, because of the filler space. The compiler knows that because it's the thing that set up that filler space. So if we say size of struct node, it'll go into its own brain and say, oh yeah, that takes 16 bytes, and it'll do the right thing. It's one of those things that if you play by the rules, everything works, and if you don't, it gets sketchy really quickly. The worst sketchiness being these kind of time bombs that don't cause problems right away, but set up things that will fail later on. And another typical consequence of that is you develop this set of code and it works great, and you develop this set of code and it works great, and now you're working on a totally unrelated set of code and you've got bugs, and you're going back and you're changing it and you're running it in GDB and you're pulling your hair out, and the problem is not with that set of code you just wrote, it's with that first set of code that you wrote and tested and decided was working perfectly 2 days earlier, right? And it set up one of these landmines for you. All right, so let's go ahead and run this. We're going to allocate space for an integer. We're going to set the thing that I points to be 15, and then we're going to say that we're done. And I forgot to include standard lib. Alright, so we're going to say ready to do assignments. So let's print out the value of I first. I is a 0. Alright, so that's just, the unassigned initial value. Now we're going to call malloc. So I'm going to say next, and I'm going to print the value of I, and I is equal to this funny number. So let me write this down. So somewhere in our computer's memory we have a variable called I. And the value of I is a bunch of 5s and then a 6670. All right. What is our interpretation of this big number? It's a 64-bit number actually. Bunch of fives and then a 6670. That is a location in memory that Malik gave us. It refers to somewhere in memory. And let's see what's stored at that location in memory. At that location, we find a 0. Okay, why is there a 0 there? It just happened to be. Right? So this has got a 0 in it. Now we're about to say star I equals 15. So let's go ahead and execute that. Well, if I look at that same location I just looked at in memory, guess what? That's got a 15 in it now. Right, hex F.
Hey, Professor.
Yeah.
So for malloc, does it always reallocate whenever you run the function, or does it somehow remember where it allocated?
And anytime you call malloc, it will give you another chunk of memory, and it's up to you to keep track of what's been given to you. Does that make sense?
Yeah.
And that's going to lead to the topic of memory leaks, which we're going to talk about in a few minutes, which is how do we deal with allocated space when we're done using it. And it's also up to us to deal with releasing allocated space. Malloc, anytime you call it, it's just going to hand you a chunk of space. All right, so when we said star I equals 15, it stored 15 not in I, right? I has still got the same value it had before, but it changed what was stored at this memory location. So I is a pointer, right? And this is the place that I points to, and this just got changed to, you know, a 15. I didn't change. I still got this value. And if you're curious, where is I stored in the computer's memory? Well, it's stored at this address, right? So 7FFF, bunch of 1s, and then E3, E8. So I is stored down here at this location, E3, E8. The contents of I is this big number, 5555, etc. And when we say star I equals 15, what we're saying is take the contents of I, go to that location, set the contents of that location equal to 15. In direction, right? So we don't set I equal to 15, we set the thing that I points to, which is this block, this byte, 4 bytes, we set that equal to 15. So yeah, the memory address is stored in a different address, basically, which can seem confusing. It's pretty rare that we're going to deal with the address of I, right? It's very common that we'll deal with the thing that I points to, though. So yeah, pointer to a pointer. And if I call malloc again, right? If I say I want 4 bytes, it gives me it gives me a different address. Well, that's not the address I expected. Right? Every time I call it, it gives me a different address. Now, when I called it from my code, it gave me address, you know, starting with a bunch of 5s. When I call it from GDB, it's giving me an address that starts with 7FFF, right? But nonetheless, these are free locations in memory that I could have stored, you know, presumably 4 bytes. Now they're separated by 16s, so it's actually allocating 16 bytes even though I only asked for 4. if I ask for 40 bytes, right, it's going to go by a larger chunk. So it's going to, give me address F60, and then F90, and then FC0, and so on. So it's giving me chunks of 48 bytes. So when your program exits, all of this memory gets reclaimed on your behalf. So when I kick out of here, all those allocs that I did, that memory goes back in the free memory pool. So you don't hose your system by experimenting. But until your program exits, memory that you allocate is in use. I don't know if I can do this or not. Let's see if I can hose my system a little. So I'm looking at memory that's available, actually. Yeah, we'll just use top. So I'm looking at memory that's used and memory that's free. And looks like I've got 4 gig of memory used. We did this a little yesterday. Alright, so there's some memory. I don't think I'm going to be able to notice this, because this is all virtual memory. But that's not bad, right? I can allocate a pretty big chunk of memory. That's 100. Whoa, is that really? That's 100 gigabytes. That's 10 gigabytes. It's a pretty good sized array. Yeah, I'm not going to notice this. It's going up slowly. Yeah, so I'm at 4048. 4043. Yeah. So it's pretty efficient. Alright, let's see. What else is in chat here? Alright. So that's our basic setup for what we're doing, right? We're going to use pointers to, we've been, playing with I, but we're really going to use pointers to a struct node.
Professor.
Yeah.
So when the program exits and all the memory is allocated again, or all the memory is freed up, does that mean that the pointer to I isn't 15 anymore? And also, like, any other thing we can think of for that?
So when the program exits, the location that I was pointing to, right, this location up here, this goes back into the free memory pool. And some other process that does a malloc might grab that location and start using it for its own purposes. Or it might stay unallocated for a while. But it basically goes back into the available pool of dynamic memory in what's called the heap. And so that 15 will stick around in memory for a while, and eventually it'll probably get overwritten. Nonetheless, it's our responsibility anytime that we malloc memory, we should return that memory to the memory pool when we're no longer using it. Now variables like I, these are allocated in what's called stack space. And in a function, when you have local variables, when your function exits, all those variables that you declared in the function, they go back to free storage, right? The memory they were using is reclaimed basically and available for other processes to use, or other pieces of your code. But memory that you allocate is different, right? This is not going to be freed up just because you exit a function that you allocated memory in. Okay, it's persistent memory throughout the life of your program. And on some operating systems, it's persistent memory forever, right? It never gets freed until the system reboots. And so this gets us into the idea of a memory leak. So a memory leak is a situation where you've inadvertently allocated memory and you haven't released it. Now, if you want to use this memory later, don't release it. If you're building a linked list in your add method, you're going to, dynamically allocate a new node and put it into your linked list. You don't want to release that memory. You're using it, right? So you're going to keep that memory in use. But when you delete a node and you change the pointers so the thing before the node points to the thing after the node, right? We no longer need that node we deleted to persist. So we would need to say, hey, take this node of memory, put it back in the free memory pool. And we do that using a function called free. So free is the counterpose to malloc. Malloc says, give me a chunk of memory. Free says, I'm releasing this block of memory. And these are the exact analogs of get node and release node from PA1. But they're handled by the Linux system for us instead of having to do that ourselves. Why did it not deplete memory? Because I didn't really allocate that much memory. Virtual memory, I don't know what virtual memory is able to go up to on here, but a few 100 gigabytes of virtual memory doesn't seem to be a lot, which I'm kind of surprised by. And memory management's a whole nother topic. We brush it sometimes in Engineering 270. When I teach that and we have time, sometimes I go through the hierarchy of virtual memory and physical memory and so on. But that's a glorious topic in itself. All right, what happens if we don't free memory? On Linux, right, everything gets reclaimed. What if your program never exits? What if this program doesn't just, exit after it said did assignment, but it sits here and it runs, forever, for the life of the computer? What if it's a web page server, right? What if it's the assess program, which is, picking up student requests for assessing their ODPs, and it never exits? If I'm consuming memory inside here and not releasing it, I can end up taking up more and more memory from the system. And sometimes you find programs like web browsers, for example, and you start seeing people posting comments like, my system isn't running very well ever since I installed such and such. I had to reboot my system. Well, it turns out, there's memory leaks in programs, and if you run a program and you just kind of leave it running in the background forever and you don't close it out, sometimes over a period of hours or days, you'll see the free memory on your system keep dropping, and it gets lower and lower and lower until it's so low that you really can't do anything. And if you exit that program, the operating system reclaims all that memory that was allocated, and suddenly your system's running great again. So we never want memory leaks, right? And part of the grading rubric from PA2 on forward is going to include taking care of memory leaks. Yeah, Word has done that in the past. Firefox had a release where they had a big memory leak, and it was notorious. And you just had to exit it out every now and then. exit out of it. So we're gonna deal with memory leaks ourselves, okay? It's very easy to get a leak, right? Because I'm allocating memory here, maybe in my add function of my linked list code, and I should release it in my delete function, which is totally different code. Sometimes we don't do that. So let me show you how you can detect memory leaks first of all. So I'll go ahead and compile my program. I'll run it. It says ready to do assignment. Did the assignment. Everything works fine. But I actually lost some memory. So there's a command called valgrind. And the way we run this is we just say valgrind and then the name of our program. And if we have arguments to put on it, we can put the arguments. Valgrind will run your program, but it will monitor memory allocations and releases. And then it'll give you a report at the end. So if I run valgrind on this simple Go99 program, I get the following message. So this was the output from my program. This was preamble from valgrind. There's my program's execution, and now here's a summary from valgrind, and it says in use at exit 4 bytes. In other words, there are 4 bytes of memory when my program exited that were still allocated. And they came from, they're in one block, so it came from presumably one call to malloc. And then some more details. Definitely lost 4 bytes. You can have nodes that are lost but still reachable, which means you still have a variable pointing to that block of memory, which you could have used in a call to free. But sometimes you allocate something else, allocate something else, and you're throwing away the pointers to those things. For example, in the linked list, when we change the thing pointing to this node to point somewhere else, once we exit our delete function, we have no reference to this node anymore. Okay, so that would show up as a definitely lost block. If we still have something pointing to it, but we haven't freed it, that would still be reachable. Any of this stuff going to cost points, right? So as soon as you have a memory leak, right, there's going to be a deduction. So how do we deal with this? Well, it's really easy to deal with it in here. So let's just release the memory reallocated. So I'm just going to free I. Why am I passing I? Because I was the address that I got back from malloc. So compile that, run it through valgrind. Here's what you want to see. All heaps blocks were freed, no leaks are possible. And valgrind will keep you from doing all kinds of things. So let's do this. Let's print out the value of I before and after we do that assignment. I don't know if this will demonstrate anything or not. All right, so before assignment I was equal to 0, after it was equal to 15. When I run this through valgrind, I get some extra backtalk here. Conditional jump or move depends on uninitialized values inside my printf function from line 11. These are warnings. You got to pay attention to these. What it's telling me is that at line 11 of my code, which is right here, I used a value in dynamic memory that hadn't been initialized. In particular, I was looking at the integer that I is pointing to. Well, it noticed that, I haven't given that a value. I haven't done something like this yet. And so it's going to give me a bunch of warnings. Use of uninitialized value of size 8. Line 11 of Go99.c inside printf. So if you start getting these, you got to deal with them. Again, it might be something that your code still looks like it works correctly in the end, but you're setting up a potential time bomb. Right? So when you run Valgrind, what you really want to see is something like this. I lost it. Something like that. All right, so we'll play more with Valgrind as the week goes on. Let's see, anything in chat? No, we're good. Okay. So let's look at some how some of this relates to PA1 and PA2. So we're going to make a struct node sentinel. That's going to be our sentinel node. And here again, I need to have some kind of consistency in my brain of what I mean when I write sentinel on top of a box. Sentinel is not a struct node. Sentinel is a pointer to a struct node. Right? Just like in PA1, sentinel wasn't a struct node, it was an integer, which was an index into an array of struct nodes. It's a reference to this node. All right. So we need to set sentinel equal to malloc size of struct node, right? And then set its next field equal to null. We're going to write an init function. You're going to write an init function that'll return the address of a sentinel node whose next field has been set to null. And our initialization is just going to look like this. And that's going to be a different looking function call from what we had in PA1. That's the only one that's going to change. So let's imagine a linked list. And it's been built and we've got pointers. And let's suppose we want to move down this list and print out the values of nodes. So I have my sentinel set up. I'm going to make a temporary pointer, which I'm going to call current, or cur. And that's going to be a pointer to a struct node. And I want to initialize current to be a pointer to this first node. And so I would do something like current equals the thing that sentinel points to, that thing's next field. And I'm going to print that current node's data field. So star cur says the thing that current points to, which is this struct node. Dot data means the data field. And then I want to move current to be a pointer to this next node. So I'm going to say current equals the thing that current points to, that's a struct node, that thing's next field. And I'm going to loop. And when I get to the end of my list, when I'm pointing to my last node, I'll print the data field. I'll set current equal to current next. Well, if this is the end of my list, that's going to set current equal to null. And so this is a good old while loop. Just while current is not equal to null. Same thing we saw before. Alright, so that's our linked list with pointers. So we'll start developing algorithms for this tomorrow, but let me give you a syntactic shortcut. And this is going to be really, really important. So this is arrow notation. We're going to end up writing things like this a lot. We're going to have a pointer to a structure. We're going to dereference that pointer. We're going to say, give me the structure that we're pointing to and give me the next field. Or give me the structure we're pointing to's data field. So if we have a pointer to a structure and we want to access some field, instead of typing this, we can type the following. Pointer, and then we make an arrow out of a dash followed by a greater than sign, and then the name of the field. There we go. All right, and this is the way that we can think of it at first, because we've encountered this before, but over time your brains will shift towards thinking of it more and more like this. And the way I read this kind of internally is, you know, this is a pointer. Take the thing it points to, give me the you know, that field of whatever it's pointing to. And so this would become, you know, current arrow data, current arrow next, sentinel arrow next. And this becomes a really, really nice way. Dash with a greater than is built in. It's part of the C language. So this is nice because suppose I wanted to access this data field right here from the sentinel. Right? What I could do is say, take the thing that sentinel points to, which is this block, take its next field, which is this, take the thing that that next field points to, which is this block, take its next field, which is this address, take the thing that that next field points to, which is this block, and give me its data value. Okay, that would give me the value of this data field starting from the sentinel. If I do this translation, this comes out as follows. And it kind of reads the way that we think of linked lists anyway. This is sentinel. Take the thing it points to, give me the next field, which is this node. Take the next field of that, which is this node, give me the data field. And for most of us, this is going to be easier to read than that. If you like Lisp, this is pretty natural to you. But otherwise, this is going to work more naturally. And as we get on to more complex data structures, we will start doing things like this. When we start working with binary trees, if we talk about balancing red-black trees, we'll be writing statements like this all the time to say, go to my parents' parents' child's parent, right? And so this is an important shortcut. And you're always going to want to use this, except like I say, when you're first working with this stuff and kind of learning it, it may help to think of it like this and actually write it out like that. But once you understand, you know, working with these structures and resolving fields within things that are pointed to, start moving over to this notation as soon as you can. And it will absolutely make your code easier for you to manage. All right, so tomorrow we will start going through in earnest some of the linked list code from PA1, thinking about it in terms of dynamic memory. We'll look at PA2 either tomorrow or Friday, and we'll also look at the GDB quiz that's been posted for a while on Canvas now. All right, I will see you next time. Have a good one. Thanks.